All right, welcome everybody to Matrix Math Day. We're going to be doing more mathematics in the world of game development. You might be like, but no, I want to just make games. I don't like math. Well, as it turns out, there's a lot of math that you need to know in order to do game dev. The good news is the math is not too bad. But it's something you still got to know. So, I remember on yesterday actually. Me and Carly was studying partial derivatives, and you have a three-dimensional surface. You have a point on the surface. You want to know what's the direction, the greatest slope is in. Guess what? You use that in a game. You put a ball on a hill. You expect it to roll in the direction of the greatest descent, right? All these things in math, they actually have uses, even though your math professors might not tell you they have uses. So what we're going to do today is matrix math. And so matrix math is, you can do a matrix times a matrix. You can do a matrix times a scalar. Those are all not what we're talking about today. Today we're going to be talking about a matrix times a vector. Okay. So we are going to be using a 4x4 matrix. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. This is something called I, the identity matrix. This is the equivalent to the identity in arithmetic. 5 times 1 equals 5. I is basically 1, the identity, or adding 0, right? So I is the identity matrix. If you use the identity matrix on a X, Y, Z location. So if we have a location in space, and we have X, we have Y, we have Z, if you're British, got some point in space, you can manipulate points in space using matrices. A 4x4 matrix is used to manipulate points in space every time you're in the matrix. Every time you are in Unreal Engine and you rotate something, you scale something, you translate something, what you're doing is you are just messing with the values in a single 4x4 matrix. You are not, it's actually a lot more simple than you think. It doesn't take any more effort to rotate and scale something than it does to just rotate it. Because the entire transformation matrix is just one single 4x4 matrix. And what happens is you put a point in, X, Y, Z, and then the transformation matrix will spit out a new X, Y, Z. Don't worry about the 1. It's just there to make the math work. And if you have the identity matrix, well, the input point is going to be the output point. So this point here, it's not going to change. You are going to get literally X, Y, Z back out. But for, it was 58. Okay, that makes more sense. So I don't remember doing this in 26. But there are other matrices that will do things like scale things. So for example, if you have the point 2, 0, 0 here, right? It's 2 east, none north, none in. And you scale it by 2, you will get 4, 0, 0. This is a scalar. Scaling, not a scalar, sorry. It's a scaling operation. You multiply it, all the points by 2. And so this point over here, which might be at 8, 4, 3, if you scale it by 2, then you end up having it be twice as far away at 16, 8, 6. You guys understand? And so if you scale every point in an object, it gets twice as big. Are you guys with me? Scaling, right? And so how do we scale something? Well, let me show you the matrix to scale something. Then I'll show you how to do an actual matrix multiply times a vector. This is a matrix over here. A matrix is a 2D data structure. A vector is a 1D data structure, and a scalar is just a number, okay? And so you can multiply a matrix times a scalar, a matrix times a vector times a vector, a scalar times a scalar. You guys know that one already. 2 times 2 is 4. Yay, you got scalar math down. Multiply scalar times vector, scalar times scalar, matrix times matrix, all the combinations. There are ways of doing it, and there are different uses for it. Today we're going to be focusing on matrix times vector. How does that work? Okay. So let me show you the matrix that you would do to do scaling. It's going to look like this: 2, 2, 2, 1, and then everything else is a 0. So you're going to have zeros filling in the rest of the place. Okay. That scales the x direction by 2, the y direction by 2, and the z direction by 2. If you want to have non-uniform scaling, all these 3 numbers can be different. If you want to scale, you know, the chair, if you widen the chair and turn it into a couch, that might be widening it in the y direction or something like that. In which case, you might do like a matrix that looks like, I don't know, 1, 5, 1, something like that. Then that is going to widen it 5 times in the y direction and leave the other 2 alone. Okay, but normally we work with uniform scaling, so I'll put that back. Okay, so how do we actually multiply a matrix times a vector? It's going to look like this. So if we give me a point in space, okay, 8, 4, 3 works for me. 8, 4, 3, 1. What is that 1 for? Don't worry about it. Just it's there to make the math work out. So the first number here is x. The second number is y. The third number is z, and the fourth number is always 1. And whenever you have a 4x4 matrix, that number is pretty much always going to be 1, 2. Makes the math work out. Okay, don't worry about it. So how do we multiply a matrix times a vector? Let me show you the secrets of mathematics, of linear mathematics, of mathematicians, how it's done. All right, so we're going to take the vector and we're going to turn it sideways like this. 8, 4, 3, 1. And we are going to multiply down like this. So we're going to multiply 8 by 2, 8 by 0, 8 by 0, 8 by, is that 6? No, that's a 0. 4 times 0, 4 times 2, 4 times 0, 4 times 0, 3 times 0, 3 times 0, 3 times 2, 3 times 0, 1 times 0, 1 times 0, 1 times 0, 1 times 0. And we end up getting something that looks like this. 16, 0, 0, 0, 0, 8, 0, 0, 0, 0, 6, 0, and 0, 0, 0, 1. So did you see what we did here? All the components of the matrix get scaled, they get multiplied by the corresponding value in the vector. So we take the vector, turn it sideways, multiply down, then we're going to add across. Multiply down, add across. And so 16 plus a bunch of zeros is 16. Get rid of that little line there. Is 16. 8 plus a bunch of zeros is 8. 6 plus a bunch of zeros is 6. And 1 plus a bunch of zeros is 1. And so the final result of our matrix times vector multiplication is 16, 8, 6. This is the x value, the y value, and the z value. And that is, in fact, what we see over here. When we scaled 8, 4, 3 up by 2s, we got 16, 8, 6. Maybe you could read if... is it doing the thing? Is it doing the thing where I can't select another thing? Great. Let me close out of OneNote and relaunch it. Never change Microsoft. Never change. All right. Can I click on it now? Cool. Neat. Okay. 16, 8, 6. Mathematicians. Okay. So that is scaling. So whatever number you have whatever number you have here is scaling of x. Is scaling of x. Whatever number you have here is scaling of y, scaling of z, and then that thing is always 1. Right. So the identity matrix, if we did all this stuff, we multiply x by 1, y by 1, z by 1, which does nothing. That's why it's called the identity matrix. So the identity matrix is just pointless. I mean, it's not pointless. It doesn't do anything. So the next thing we want to do, scaling is easiest to understand. The next easiest to understand is translation. So these 3 parts of the transformation matrix are used for scaling in the x, the y, and the z directions. So if we want to move this point east, let's use this point here. We're going to move this point east by 5 and down by 10. then we're going to put a 5 and a -10 and a 0 because we're not moving in the z direction. And we're going to end up with a point at 7, -10, 0. So the transformation matrix for that is going to look like this. Just use the identity matrix. We could add it to that one if we wanted to scale and transform at the same time. Translate, sorry, at the same time. But I'm just going to show you translation on its own. So these three numbers here mean how far we are going to translate the point in the x, the y, and the z direction. So we're moving at 7 east, 10 south, and 0 in. Okay, and we're going to multiply these by our point here, which is 2, 0, 0. 2, 0, 0 with a 1 at the end, as always. And when we multiply 2, 0, 0, 1, multiply down, add across, we are going to get, sorry, we wanted to move it, sorry, we wanted to move it right 5. 5, right 5. We're moving it to the right 5 and down 10. I was looking at the answer, not the movement. Okay. So we're going to multiply down, add across. So 2 times 1 is 2, plus 5. I'm going to write the output over here. Equal to 7. Multiply down, zeros all across down. Adding across is -10. Zeros all the way down. Adding across is 0. Ones, adding across, we get a 1. And that is our answer. So you can see that this transformation matrix here takes as input the point x equals 2, y equals 0, z equals 0, and returns as output this value over here. X is 7, y is -10, z is 0. Okay. You guys understand? So we now know how to scale. We now know how to translate. Okay. Now we need to do rotation. Okay. So rotation involves the powers of sines and cosines. You can rotate a point around any of the axes, right? You can rotate a point around the x-axis. You can rotate it around the y-axis, which goes this way. Rotate it around the z-axis, x-axis this way. Z-axis is that way. Y-axis is. And in real life, we call these roll, pitch, and yaw. Okay? So if you're an airplane, roll is this, right? You tilt the plane to the left or right. Do a barrel roll. The plane rolls, like that, right? Pitch is like looking down or looking up. So when the plane pitches down, the nose goes down. When the plane pitches up, the nose goes up. Roll, the plane tilts left and right. And then yaw is like when you turn in your chair. I'm not tilting my head up and down. I'm not rolling my head left and right. I'm yawing right now. I'm not yawning. That's what you guys do. I'm yawing right now. Yawing is when a plane goes like this, which you use the rudders for on a plane. So, why did it never occur to me that rotations are sine and cosine? Sine and cosines are yeah, it's like, you got like your unit circle or whatever, right? And so if you have a point here and you want to rotate it 45 degrees, where's the point now? Is that the sine of 45 degrees and the cosine of 45 degrees? Okay. If you want to rotate it 90 degrees, you're at the sine of 90 degrees. What's that? Maybe I'm doing these backwards. You're at the cosine is x. Yeah, cosine's x. And then the sine is y. So the x value is equal to the cosine of theta, and the y value is equal to the sine of theta. So if you rotate 90 degrees to the left, the cosine of 90 is 0, the sine of 90 is 1, and you're at location 0, 1. And if you have a non-unit circle, then you just scale that by however far away the point is. So and if you do 180 degrees, now you're at cosine of 180, which is -1. Sine of 180 is 0, right? So this is point -1, 0 over here. So yeah, so the cosines and sines are used for rotations. And so the only question is which axis are you rotating around? So in this case, we're kind of like rotating, metaphorically speaking, around the z-axis, right? So rotations around the z-axis involve x equal to sine of theta, y equal to sine of cosine of theta and sine of theta for x and y. If you're going to rotate around the x-axis, then it's going to be a different pair of those. And so rather than asking you to memorize all this kind of stuff, we just look up the transformation matrix 3D, and there are cheat sheets that will tell you the rotations around each one of the axes. So if you're rotating around the z-axis, the x value is going to be the cosine of theta, right here. And then, well, it gets a little complicated, but yeah, you basically put those values in. So if you want to do a 90-degree rotation around the z-axis, then you are going to have a transformation that looks like this. So 90 degrees, cosine of 90 degrees is 0. Negative sine of theta is -1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. So if we're going to rotate the point 5, 3, so if we have the point 5, 3 here, we're going to rotate them 90 degrees counterclockwise or clockwise. Let's find out which way it is. I don't remember off the top of my head. We'll find out. We're going to rotate it 90 degrees. Let's find out where it ends up with this transformation matrix. So x is 5, y is 3, z is 0, and we always have 1 at the end to make the math work out. And we're going to multiply down, add across. So this guy becomes a 5, this guy becomes a -3, this guy becomes a 0. We add across, we end up getting -3, 5, 0, 1. We end up getting 3, 2, 3, 4, 5. Yeah, so it is in fact counterclockwise. So we got a rotation of 90 degrees to a point of -3 and 5. Okay. So that is a 90-degree rotation around the z-axis here. Okay. Can you combine all these things together? Yeah, you can. So you can do scaling, and you can do translation, and you can do rotation all at the same time. So you can just stuff them all into a single transformation matrix, and then you can do them all at once. And so all you ever need to do is one 4x4 matrix times a 4x1 vector to do basically any of the basic transformations in 3D for translation, rotation, scaling. It's just one. And are CPUs optimized for this? Oh yes. Oh yes, they are. Intel CPUs have very specific, like, this takes 4 floating point numbers and multiplies them all by, the same thing and adds across. Like, there's very specific instructions in CPUs to do very specifically a 4x4 matrix multiply. Because it's the basis of 3D games. If you have a 2D game, you actually use a 3x3 matrix and a 3x1 that's XY, right? If you're just doing like Mario or something, the matrix is actually 3x3, and the vector, instead of being 4x1, is 3x1, because you just have XY, you don't have XY, Z. And all the math basically works out the same. So, monitors are cheap. GPT, CPU reference. Interesting. So, interesting. Can we open this over here? Can't save. All right, let's see what you got. Swing rotations. They're going off the edge of the screen. Got barycentric interpolation of the colors going. Yeah, looks good. Looks good. Okay. Let's see, green, red, blue. Yep, nice. Awesome. Okay, so maybe we'll do one more, and then we'll kind of combine everything together. Like maybe we'll do a rotation and a translation. Actually, let me see if you guys can figure it out. So let's say that I want to do a rotation of 180 degrees around Z. And I want to move 10 in the X direction and negative 20 in the Y direction and plus 30 in the Z direction. Can you guys construct for me a transformation matrix on chat that would allow this transformation to happen? Wait a second. I'll go ahead and pause the stream. All right, so if we wish to combine a rotation and a scaling. Now, there is a sort of order of operations to these things. So if you like want to move it, then rotate it, that's different than rotating it and moving it. I'm not going to worry about that right now, though. So what we're going to do is have a -1, 0, 0, -1, 0, 0, 1, 0, 0, 0, 0, 0, 1, 10, -20, and 30. And then if we're going to take the point 5, 3 again here, and we're going to rotate it and move it. Let's see what we get. 5, 3, 0, 1. And multiply down, add across. That turns into -5. That turns into -3. That turns into 0. Then we add across. We get 5, -23, 30, and 1. 5, it's like down here somewhere. -23, and then 30 in. So it rotated over here, then it got moved 10 east, and yeah. So yeah, so it got rotated and pushed around, and it ended up over here somewhere. So that's why it's usually easier to just do one of them at a time, so you can kind of demonstrate the principles of it. So that is a matrix times a vector. There's also matrix times scalar. This one's extremely complicated and difficult. So if we have just multiply the numbers in it. I'm kidding. What about a vector? What about a vector times a scalar? Even harder. Multiply this by 2. See, the only tricky part is that one should stay at 1, right? You get 20, 40, 60. 1, maybe? Yeah. Technically, that turns into a 2, but, you know, technically it turns into a 2. So anytime you multiply a vector times a number, just by a scalar, all the values scale up. So it's just like, except this little bit here, we pretend doesn't exist, maybe. Okay. Matrix times a scalar is just every component by the scalar. Yeah, and same for vector times scalar. It's pretty easy, pretty straightforward. If you have a vector that's like this, and you scale it by 2, it's now this, twice as far away. It's pretty easy. What about yeah, it's not worth noting, I think. What about let's start out easy. What about dot product? So if we have a dot, so we've been doing dot product with normalized vectors, right? So if you have a normalized vector here and a normalized vector here, the dot product of it is equal to the cosine of the angle between them. Okay. And so we use dot product very commonly to tell our two things looking the same way. Cross product is the sine of the angles. Scalar cross product is the sine of the angles. Dot product is the cosine of the angles. That's all they are. But you do not actually have to do dot product with a normalized vector. Okay, and cross product, like for your current assignment, you are not using normalized vectors, right? If you have a thing here and you have a thing here, the cross product is going to give you the angle of the parallelogram of this. So this is the, not the dot product, sorry. This is the cross product here, is going to give you the angle, sorry, the area of this parallelogram, which You don't normalize it, because if you did, then you would lose the area, right? So sometimes you normalize things. We normalize the cross product to just find out if they're pointing at which person's to the right, which person's to the left. We'll use a normalized vector here, unit length here, and the cross product just returns the sign of the angle between them. So if they're pointed the same way, you get a 0. If they're pointed to the right, you get a positive number, and if they're pointed to the left, you get a negative number. Depends which one's first, which one's second. So whether it's positive or negative is sort of arbitrary. Like, is this A and this one's B, or is this one A and this one B? Whichever one you pick, you're going to get the opposite sign. You know, one's to the right, no, he's to the left, depending on your perspective. It doesn't matter. Okay. So, do you guys understand cross product, by the way? So cross product is basically just the sign of the angles between them. Now, if you don't normalize them, then you're going to get the length of A and the length of B multiplied in as well. That's going to give you the area of this quadrilateral here. It's parallelogram. Okay. So if you don't normalize them, then you're going to get an area. That's why we normalize a lot of times, because all we care about is the result of the sign, basically. And the equation for this is in 2D space, at least, is x1 y2 minus x2 y1. That's the scalar, which means it gives you a number, a single number, the scalar cross product. The dot product also, we don't necessarily have to normalize the vectors. There are cases where we don't normalize them. So for example, if you just have vector A here and vector B here, and you don't normalize them, then the answer you get is the cosine of the angle between them times the length of A times the length of B. Okay. Betancourt was posting some ray tracing code online, and they were not normalizing the distance vectors. And I'm just like, I don't know if you know what you're doing. But like, he was just checking to see if the sign was positive or negative, in which case it doesn't matter, because if it's positive, that means it's pointed towards. If it's negative, it means it's pointed away. And he was just checking to see if the thing was pointed towards the light or not. If it was pointed towards the light, you can see the light. If it's pointed away from the light, you can't see the light. You don't light. So cross product of 0 is the sign being right or left. Yeah, depending on which one's first. You know, and so, you know, for your barycentric, like, maybe you absolutely value it, just so you don't have to worry about which one's first. And the dot product is going to be x1 x2 plus y1 y2. So if these values are not normalized, you will get the full cross product equation here. So what is that useful for? A big thing dot product is useful for is projection. Okay, so we all know when we're talking about projecting, right? It's when you take your own personal beliefs and believe that other people are believing the same thing as them, right? That's what we are doing here with our dot product. So if we've got A, it's over here, and we got B, it's over here. What the dot product will do is actually let us project A onto B. Okay, so this is useful for like shadows. It's also useful for like if you have a circle and you want to know what is the nearest point to this line here that we'll call B. Well, if you project A onto B, you get the nearest point to the circle. Cool. All right. So this is just the dot product. It's literally yeah. So you might, what does that tell you? It's going to tell you what is it going to tell you? It's going to tell you, let's see, you need the length of A onto it. Yeah. So what you're going to do there is you're going to have B be a unit vector. Like, you're going to scale B to 1. And then what this is going to be, it's going to be the length of A times the cosine of theta. And that will give you this point right here. Because you take this is going to give you a number. It's going to give you like 5.6 or something. And then you scale B. This is the unit B vector here. So you're going to take 5.6 and multiply it by the normalized B vector, right? And that'll give you the point that A projects onto B, like a shadow. Okay. So that is really useful as well, because it's not only useful for like shadows and things like that, but like for finding the nearest points to things you project onto a surface. Silhouettes, like there's a lot of things where you project something onto something. Heads-up displays, you have an object in the world, and you've got your 2D plane here. You project the object onto the plane, and then you add up a little bit in the screen coordinate system, and you put the health bar there. So if you want a health bar floating over an enemy in the world, you project the enemy onto the screen. It's like casting a shadow. Do you guys understand what I mean by like casting a shadow? Like if you have like something like that. So you're projecting the shape onto a surface. And so that would be a 3D to 2D projection. The dot product here we're doing is a 2D to 1D projection. So we're projecting a thing in 2D space onto a 1D line. We're saying, where does that point, like if we have the sun up here, the sun's up here, it's very bright. Where does this shadow of this object here go? And it's going to cover this area here because we project everywhere from here to here as a shadow onto B. And so you just compute the cosine of the angles between them. That's the angle. Compute the cosine of the angle and multiply it by the length of A. Whatever the length of A is going to be, let's say, 5.6. So 5.6 times the direction of B, the normalized B vector, is where the end of the shadow is going to be. And that's useful for finding nearest points. It's useful for a lot of things. So dot product, cross product, those are your tools. What you're going to be quizzed on today. You're not going to have homework because I want you guys still working on your coding assignments. I'm going to give you a math quiz for today. So I'm going to see, can you guys recognize a transformation matrix that, yeah, you haven't done a quiz in a while. Can you recognize a transformation matrix that does rotations, translations, scaling, dot product, you know, all this kind of stuff. You basically have to have perfect and complete mastery of what I talked about today. You'll be fine. All right. You guys all follow along? Or distracted at all? Talking about things? You guys good? Any questions about it? Ask now. What? Your assignment for today is to take a math quiz. I'm going to give you a math quiz on this. When I started working in the industry, they handed me a book of math, basically. Actually, two books. One was, I think, the OpenGL Red book. And then the other one was just basically a bunch of linear algebra mathematics. And they're like, learn this, you know? And I'm like, I worked at the company for a week, and then I went on vacation because I'd already booked a trip to Puerto Vallarta. And I actually took the OpenGL book and the math book with me. And I'm like, I just remember sitting on the beach in Puerto Vallarta, beautiful palm trees and margaritas, and just like sitting there reading about linear algebra, feeling like a nerd, but feeling like the coolest nerd on the planet, playing beach volleyball and reading linear algebra at the same time. It felt nice. It felt nice. Working on my tan, working on my math skills. It's a good combination right there. Game Dev should have this as a math class in the description. Games are math. Like at UC Santa Cruz, apparently they don't teach math. According to one of my students who graduated from there. So I have Jack Sims, who was just, I think, here earlier. He's at Santa Cruz right now as a math major. So we'll find out. We'll find out if they teach this stuff there. So I don't know how you could do math. Sorry, I don't know how you could do games without math. Like they're like fundamentally like you can't do anything if you don't have like the basics of linear algebra under your hood. Okay, see you guys, and we're gonna be ready for 50A in 1 second. Peace.